So what have we got here?
So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. You see, this is quantum trapping.
That's amazing.
As long as it's
so
cold,
it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnetic field in 3 dimensions, right?
Yeah, exactly.
And that
and
pivots.
You see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
it stays there on the X and Y, but not on, it pivots on the...
Yeah, on the axis of the magnets. You see, if I can move it on the side, it will again pivot around the axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing. Can you put it on the track for us?
Yeah. I just levitate it above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it at an angle and it would still fly around.
Yeah, I can do it like this, and it will just go around like this. Because I go and put it at different height, and then like this.
And lock it at the height.
Lock it, yeah, different height, different configuration.
Right.
And I can even lock it at opposite way. If you could just hold for a minute. High. I'm doing the same thing. I'm locking it upside down, and then it is suspended.
Fantastic. Okay.
I've got a degree in physics from UC Berkeley, and I've had a lifelong fascination with the true nature of reality. And I actually believe that's probably what propelled me to have some of the experiences that I had, which demonstrated that there are sometimes these remarkable shifts in reality that can occur, and that what we call quantum jumps are not just something that happens on the quantum so-called scale, but they can happen at any level of physical reality. I had a fairly normal stretch of time in my life when I was doing normal research. I had a job in the banking industry. When things started changing was around 1994, when I started really noticing remarkable changes in reality that was following a Kundalini awakening, which was a change in my inner energy. It seemed like just being flooded with so much energy that it was incredible. And sometimes seeing so much light. I felt blinded even with my eyes shut. There was so much light around me. During it, and then also after, I was noticing that I'd sometimes be spontaneously aware of things happening in remote locations, like spontaneous remote viewing, or 360-degree vision that I can see all the way around me at quite a distance and outside the walls of the house. So it was really startling. And then ever since then, I've had the ability at times to have exactly the same experience again. I didn't test it so much by doing those kinds of things of going to see if what I saw was real, but my daughters would try to sneak up on me and they never could, especially after that. It was just impossible because I could see them before they got to me. I've had other things happen where if I'm daydreaming, I've been observed in 2 locations. I know I'm in one place where I'm daydreaming, but I'm observed somewhere else. So there's a bilocation that can occur. I'll give you an example of one morning when my daughters were quite young. I needed to go wake them up each morning so they'd go to school. And they were too small to open the curtain in their room. It was too heavy. So I would go down the hall, I'd turn the light on, and then I'd walk to the window and they'd say, "Good morning, girls," and I'd open this very heavy curtain that would then go up. And one morning, it was a cold morning, I didn't want to get out of bed right away, and I was still thinking about dreams and daydreaming a little bit. And in my mind, I was daydreaming that I walked down the hall, turned on the light, said, "Good morning, girls," opened the curtain. I thought, well, wouldn't it be great if it was that easy? But then I hear noises from their room, and then they come running around the house, and they're like, "Mom, Mom, where are you? And then, Mom, what are you doing back in bed? I never got out of bed. And I said, what? What do you mean? You just saw me? And they said, yes. I said, where was I? And they said, in our room. And now I'm jumping out of bed and I'm running to go see what happened. And their light is on, the window curtain is open, and nobody else could have done that. It only could have been me. And I know I didn't, so I experienced I'm in bed. They experienced I was there. So that was what a bilocation felt like. And for me, daydreaming and just sort of wishing I was there. The other time it happened, I was daydreaming and wishing I was somewhere and someone saw me there. So I've done this twice. And it feels great. It's just feeling like, I wish I could be there. And then guess what? Maybe you are. So after this experience happened, I immediately looked up to see what could explain these kind of experiences. And I found out that throughout history, people have had these kinds of experiences. It's really quite normal. And it's something that is considered often something that's typical for a shaman or someone who is the healer for a community, because people who have that much energy can help to be a conduit for changes in reality. And so that really got my attention about how you can change reality, or how all of us do that. For me, the most interesting thing that I learned about physics was quantum physics at UC Berkeley. I loved my classes in that subject matter. And after my Kundalini awakening, I came to realize that a lot of the answer to what is the nature of reality seems to be held in the mysteries of quantum physics, which, although we can work out the mathematics and we can solve equations and we can even build atomic bombs and nuclear power plants, we don't exactly think the way quantum physics shows us that the world really operates. And what's so wonderful and mysterious about the quantum physics and quantum mechanics is that when we look to see what are these building blocks of matter, we find that at the very center of the very smallest, inseparable, indivisible particle, which would be like an electron, if you can't get any smaller than that, then that qualifies as a quantum particle. Those little electrons can actually be observed to be in one place, and then it's like they vanish. They can change an energy level and show up instantly somewhere else. And they do other things also. They can be connected with one another, entangled, and when one is affected and its spin is up and the other one's spin is down, if you observe one, as soon as you make an observation on one that's entangled with another, they both flip at the same time. These entanglements are now being tested in laboratory conditions around the world as people are building quantum computers. There's been a race, like a gold rush, to see how fast we can find this information and these new technologies. So diamonds and large things that you can observe in your hands are being entangled. They're showing entanglements that are holding together at greater and greater distances. So we can tell, obviously, throughout the universe, there can be an entanglement with one particle right here and another particle in an entirely different galaxy, great distances away. So there seems to be no limitation on the distance. When we look at space and time, then we start recognizing that humans have a unique experience with space and time. And what we think is true for everything may not be true for everything, but may more be a facet of our humanity and the way that we are set up to observe reality.
Hello, this is Cynthia Su Lárson with RealityShifters.com, and I'm welcoming you today to the quantum age. You might be familiar with the Stone Age, the Bronze Age, the Iron Age, the Industrial Age, the Information Age, and you might be wondering, if we just started the Information Age, how is it possible that we could already be in something new? And if you're noticing how those ages each corresponded with a form of technology, then I think you know where I'm going with this today. Just as the Information Age was a complete revolution from the Industrial Age, so that someone writing books like I do, who would have used typesetting and typewriters in the Industrial Age, now would use computers such as laptops. And you've probably heard that there's a lot of research going on right now with quantum computing. If you haven't heard about it, then this is something I'd love you to take a look at, because this is what prompts me to welcome us right now into this exciting new age. I'm going to show you a picture of something called the D-Wave 2, and it's just a little black box here that you can see. This little black box has brought a price of $10 million for a couple of companies and organizations that have purchased it, including Google. And this new device will be going online, working with the Quantum Artificial Intelligence Lab at Ames Research Center in September 2013. So this is really our first step forward into the quantum age, is this very beginning introductory quantum computer, which might be analogous to the ENIAC computer that ushered in the Information Age back in 1946. So what's so different right now, and why is it that one kind of computer, such as a quantum computer, would be considered a whole step forward on such an exponential scale that it's worthy of an entire age being named after it? And what's so special about it is the qubit, the quantum bit. With existing classical computers from our Information Age, we've got bits that are either zeros or ones. They cannot exist in both states at the same time, and therefore they give us the sense that information can be stored, can be copied, and upon this we depend entirely for all of the information contained in libraries that we used to keep on books on shelves, so that if the libraries in Alexandria, for example, were burned or damaged, there would go a wealth of history's treasures, information treasures. Right now, those treasures of humanities, for the most part, exist in bits and bytes stored on computers. And a qubit, a quantum bit, is extremely different. It is as different from a classical computer bit as that classical computer is from a typewriter. And here's why. The qubit, the quantum bit, is capable of containing information which exists in multiple states simultaneously. So every single qubit, every single little piece of information that could be either a 0 or a 1 is a 0 and a 1. Could be just the 0, could be the 1, could be both. Now this may seem very simple and like who cares about that, but as soon as you've got more than one qubit gathered in any place, something super amazing happens. So if you've got two qubits, and they could be separated across a very great distance, you know for sure that to measure one of them you'll get a random answer. And that random answer would be either the 0 or the 1 in our very simple example. If it is entangled with another qubit, and this entangled qubit gives us an answer of 0, for example, we'll know for sure that the other qubit that we're not even measuring right now is definitely in the opposite state. So for this very simplistic example, that would be a 1. You can think of it like flipping two coins, and you've got them separated across a great distance, maybe in different rooms in a house. And if I'm flipping a coin in one room, and it happens to come up randomly heads, then I'll know for sure that the entangled coin in the other room is going to be coming up tails, which is the basis for the phenomenal power of quantum computing. This just touches on it. Actually, quantum computing is amazing because it's taking use of all of the spooky action at a distance properties of quantum physics, everything from quantum teleportation, quantum superposition of states, quantum coherence, quantum entanglement, and it's using it for practical everyday life. This will in turn have a huge effect on humanity, just as the information age has transformed our lives. There's hardly a person alive right now in the civilized world whose life has not been touched by this information age. And the same thing will be true of the quantum age. So even if you don't understand what a qubit is, you will start recognizing increasingly that the ideas behind quantum computing are in everyday life. So for example, when it comes to something as seemingly far out as quantum entanglement, you'll notice that that explains the kind of intuition we so often have, that we'll really know what's going on with another person even though we're separated by a great distance. With quantum teleportation, this is something that's being observed in quantum biology, in everything from our noses to what's going on with birds' sense of direction when they seem to have an unerring sense of which direction to go.
A lot of people, if you ask them enough questions, you can find a moment when they had an experience of awe as a child, which something made them want to be a scientist. I had several. I was very, very interested in animals as a child, and I remember one of the things that fascinated me was homing pigeons. I used to go with my father to the local railway sidings, where every Saturday morning hundreds of baskets of pigeons came from all over England, and the porters at the station, at a fixed time, they'd take out their pocket watch at the right time, they'd release them, they'd open these pigeons would fly up into the sky, head off in all different directions all over Britain. And I used to help them open these baskets and release these pigeons. And I was just fascinated by the birds themselves and how they found their way. I think, though, when people get absorbed in writing grant applications and in day-to-day life in the laboratory, or recedes into the background, and there's something in the spirit of modern science which, on the one hand, has opened up whole new perspectives for wonder, but there's something about the spirit in which it's done that rather diminishes wonder. You know, it says all that stuff's just sort of stuff from the past, we've now figured it out. As soon as you think we're so clever because we've figured it all out, it does have an awe-diminishing effect. And instead of a recognition of that greater interconnectedness, which I think the mystic state is about, it's about a feeling of connection to something greater than oneself, not just an idea, but an experience of that connection. I think that for many practicing scientists, that doesn't happen very much on a daily basis in the lab. but maybe it doesn't happen very much on a daily basis for most people.
Well, I think it's true that our capacity for awe, I think, is perhaps the greatest when we're young. And that gradually, with the onslaught of responsibilities, problem solving, education, and often, unfortunately, religion, that childlike capacity in us gets somewhat squelched.
Thoughts about what we were talking about earlier, but not so many about fun. I don't want to go back necessarily.
Well, what is your conclusion after all what has been discussed the last 2 hours, for instance, about consciousness?
Well, it's just that starting with this, and we got into the whole thing about internalization, machine metaphors, breaking down into little bits. And my feeling is, you see, that we're leaving huge things out of the puzzle. They may or may not be related to these, the magic tissue or wonder tissue of quantum theory, which I liked very much what you said, Freeman, about, you know, Dan may not want it in biology, but physicists deal with it all the time. My own feeling is that there are huge areas we don't understand about human and animal behavior, implying forms of interconnection and causal factors, maybe physical principles, that we haven't yet taken on board, and we're just not going to get anywhere solving this like a jigsaw puzzle with several missing pieces. However long we go on, we're not going to solve it. So my approach is to try and find what these areas might be and design experiments where one could find out more about them. One area, let me just mention one, in the realm of animal behavior, namely the homing of pigeons. Now, nobody knows how pigeons do it, and every seemingly reasonable hypothesis is being tested to destruction. We're now in a position where it's just, I think the evidence points to there being some completely unknown means by which they do it. Some form of connection between the pigeon and its home that we haven't taken on board in our model making.
Don't like the evidence behavior of magnetic particles in the head? And
well, this is what's satisfied. It's a pabulum for the last 20 years, magnetism. For the magnetic particles may exist in the head. The pigeons may be able to measure the dip of the magnetic displacement. You know, you displace them north, the needle may, the compass may dip. Move them due east or due west, the dip's exactly the same. The magnet won't help them in the slightest, even if they've got one. And
how do you know they're working only on dip?
This, well, even if they have a compass, if it's a compass,
maybe it's a compass.
All right, give you a compass, parachute you into some unknown area. You've got your compass. Can you get home?
I can get close enough to home until I pick up other signals, which is apparently.
Can you without a map?
Oh, I have to know where I am relative to where I've been.
Of course, that's the problem.
Well,
how do you know where you are relative to home?
You've migrated there once before. No, I doubt you could just take a pigeon in an airplane and drop parachute it randomly somewhere. But if you're talking about...
You can.
Oh, really?
This was done in the Second World War, yes. In the Second World War, pigeons were taken routinely on Lancaster bombers. From the British Royal Air Force Pigeon Corps supplied these pigeons. They were taken on Lancaster bombers. And the idea was if they were ditched in the North Sea on the way back from a sortie in Germany, then the navigator had released the map reference. They tie it onto the pigeon's net and let it go in case radio contact was broken. Thousands of lives were saved by these pigeons. Some were released in the middle of the night in freezing fog, 100 miles from land, and they got home. The really outstanding ones were awarded medals, and the record of these can be found in an amazing book called Pigeons in Two World Wars by Colonel Osman. And the meritorious performance list has about 500 examples of astonishing feats. They were literally dropped out of planes in the middle of the night, sometimes in the middle of the winter, in freezing fog, and they got home the next morning, and lives were saved.
Suppose that you had a very simple strategy, that you flip a coin, and you either fly due west or due east until you hit land, and so half of them then will come west and would arrive at England, and the other half would arrive in the Netherlands.
You have to record the ones that don't make it, which
but the point is, they do. They first of all, they observe the vanishing direction.
The point is, the ones that make it get the medals, and the other ones you forget about.
But in experiments, there's been hundreds of experiments done. You see, every one of these ideas has been tested by serious researchers over long periods. And cloudy days, you know, they've been released on cloudy days. They've been released with their time clock shifted 6 hours or 12 hours by keeping them in artificially displaced day lengths for weeks. All these pigeons can home. They can home with magnets strapped on their wings or with Helmholtz coils over their heads.
With blindfolds on?
Yes, frosted glass contact lenses. They've been released up to 200 miles away, and they flop down within a quarter of a mile of the loft. Many of them collide with telegraph poles near the loft, but most of them get home to the home regions. And I have a pigeon loft in Britain. And the key experiment, you see, all these theories, they see landmarks, the frosted glass contact lenses rule it out, the cloudy days, the time shift, the magnets on their wings. Every one of these seemingly reasonably remember the way out on the journey. That's been tested with pigeons anaesthetized, taken in rotating drums by incredibly devious routes. When they come round, you release them, they fly straight home. Well, all these theories have been tested. There's been years of research. Yes, they've had their nostrils blocked up with wax, they get home. They've had confusing smells like turpentine put on their beaks, they get home. And just in case that doesn't work, they've had their olfactory nerves severed, anosmic pigeons. Those get home. If some don't fly at all. But if you use then to overcome the idea of non-specific trauma, they've had xylocaine sprayed on their nasal mucosa, a local anesthetic. Those pigeons home straight off with no delay. It's a fascinating literature. For 30, 50 years, 100 years, Charles Darwin suggested the idea in his paper in Nature in 1873 on the origin of instincts, that they remember the way out, and that was the first theory to be tested. Every seemingly rational theory has been tested and tested and tested. And we've now reached a point where all of these have failed. We're in the realm of epicycles now. People are saying, oh, well, it's not any one of these in particular, but knock out 2 or 3 and the others somehow take over in an unspecified combination. Now, my experiment is designed to test this theory to see, I think there's an unknown factor involved. I don't know what it is, but I think the pigeons are somehow linked to their home.
Today I'm talking with Dr. Jim Tucker, author of Life Before Life, about the subject that some people call loosely reincarnation. You have the birthmark cases and the cases where kids are injured. Several of your cases dealt with children being born without fingers or toes, but they had recounted it in their previous life. That's how they died. Can you give us one of those
that's
cases?
right. I mean, there are a lot of cases. Ian read a book of over 200 such cases of kids with birthmarks and birth defects that match wounds, usually the fatal wounds that the previous person experienced. So, for instance, there was a little girl who recalled the life of someone who got his fingers chopped off as he was being murdered, and then was born with very deformed fingers. There's another little boy who talked about being born in another village who had lost the fingers of his right hand in a fodder chopping machine, and then he was born, his left hand was fine, but his right hand didn't have full fingers. There's also a little girl, a case where the previous person had had skull surgery just before dying, and this girl was born with this band going around her head.
Very unusual on the back of her head.
Yeah. Very unusual, yeah.
Well, as you look at this, and you've studied a lot of the cases, and it goes back into the 1960s with Dr. Ian Stevenson, who was your mentor.
Yes.
You've detailed many, many cases. What does this say about the nature of our universe? We're not basically physical beings. Our brain is not the basic component, or is it what you call consciousness?
Yeah, well, it's certainly, I mean, the cases provide evidence that memories and emotions and sometimes even physical traumas can survive the death of the brain and carry over into another life. So that means questioning the whole materialist outlook that mainstream science has, that the physical world is all that there is, and that consciousness just sort of evolved accidentally as our brains evolved. What these cases, along with work in a lot of other areas, suggest is that there is more than just the physical universe, that there is this factor of consciousness that seems to be able to function separately, at least at times, function separately from a functioning brain.
So let's get back to 2012 Enigma for a minute. Most of you have seen that video. You may remember that I discuss an experiment that was conducted in which a tiny, what's called buckyball, was shot through a grating, and the grating is 100 nanometers wide. The buckyball itself is only about 1 or 2 nanometers wide. It goes through the grating and it turns into a wave. The buckyball itself, which is supposed to be a macroscopic object, goes through this little slit, and for whatever reason it turns into a non-local wave. Now again, I talked about the experiment where buckyballs are shot through a 100 nanometer grate, a little tiny slit. They turn into a wave just by hitting the grate. It's like it makes them flip inside out and go from space-time, where they're a particle, into time-space. That solid particle, which has 120 atoms in it, it's not just like some tiny little thing. It's a ball. It's got structure. It's got form. It's got shape. It literally popped out of our space-time entirely. It flipped over into a realm where time is three-dimensional, space is one-dimensional, and it smears out. It's partly in the past, it's partly in the present, it's partly in the future. And in that state, it looks like a wave because you can't measure where everything is anymore. So now get a load of this. The DNA molecule is only slightly wider than a buckyball, which means the DNA molecule is also subject to quantum effects, in which the molecules within your DNA are phasing between being here in space-time and being in time-space, where they actually are stretched out through linear time. And they're sensitive to all the other energy fields around them.
My name's Джим Аль Kalili and I'm a professor of physics at the University of Surrey. It's very exciting for me working with John Joe McFadden to bring together the leaders in the field of quantum biology. We've been hearing at this workshop about a number of different areas of biology where it does seem as though quantum mechanics is playing a vital part. And so everything from how we smell to how birds navigate using the Earth's magnetic field to the way DNA might mutate. Quantum mechanics seems to be playing a very important role, and it's only now that biologists are starting to do the clever experiments and the quantum physicists are starting to be able to do the calculations to test those ideas. Another area which I'm very interested in and carrying out my own research is to investigate whether quantum tunneling plays an important role in mutations of DNA. Within DNA, the way the two strands of the double helix are held together are hydrogen bonds that are the rungs of the ladder, as it were. Within hydrogen bonds, protons, the nucleus of a hydrogen atom, can possibly quantum tunnel from one strand of DNA to the other. If this happens, under certain circumstances, the DNA can mutate. This is where quantum mechanics, that strange theory of the subatomic world, comes together with molecular biology to see whether some of these stranger features of how atoms and molecules behave, things like quantum tunneling, entanglement, and quantum superposition, can play an important role inside the warm, messy, complex environment of the living cell. One of the most fascinating and interesting examples is the migration of the European robin. These birds travel south from northern Europe to the Mediterranean each year by sensing the Earth's magnetic field. But they don't do this with some sort of built-in magnet or compass.
It turns out the most likely scenario is one based on quantum mechanics. That inside the retina of the robin's right eye, not left eye, they've ruled that out with experiments, inside the retina of the robin's right eye are proteins, tiny molecules called cryptochrome, that are sensitive to light, because that's why they're in the bird's eye, in particular light with blue wavelength. Now, sunlight has all colors of the rainbow, all wavelengths, but particularly blue light has a particular energy, and what that does is knock an electron from one of the atoms inside this cryptochrome protein. And that electron will jump far away from its partner that it was spinning with. Now, these electrons their fates are intertwined, they're entangled. And yet, when they move far apart, they remain over distance somehow in instantaneous communication with each other. And it's when they move apart that distance means the action of these atoms is sensitive to the changes in the Earth's magnetic field. And any changes will change the different chemical reactions that these proteins will produce, sending signals to the brain, allowing the bird to know where it is and which direction to move in.
So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment, atoms, okay, get ready, one at a time, we're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you. Quantum mechanics is the most powerful theory in the whole of science. And as a physicist, I mean, okay, the biologists may disagree, but it beats Darwin's theory of natural selection with one hand behind its back. Because quantum mechanics underpins so much of physics, pretty much all of modern chemistry, and therefore potentially biology. Without quantum mechanics, we wouldn't have electronics, we wouldn't understand what a semiconductor is, we wouldn't have lasers, we wouldn't have most of modern technology that we use today if quantum mechanics wasn't right in explaining the rules of how the microscopic world behaves and how atoms fit together. And yet, at its heart, it is incredibly mysterious.
But at its heart, quantum mechanics is strange. So strange that one of the founding fathers, Niels Bohr, once said, if you're not baffled by quantum mechanics, then you haven't understood it. You have to be. You have to think, how can that be? That's, if you think, yeah, okay, yeah, I get it, you haven't got it. Because it really is ungettable at a sort of common sense level. It really is strange. Quantum mechanics really does say that an atom can be in two places at the same time. One atom. Weirdly, when you look to see which places it really is, it'll disappear in one place and pop up in the other. So well, how do you know it was in two places at once? We can design experiments that will prove that had it not been in both places at once, you wouldn't get the results that you'd see. An electron, the tiny particle that orbits around an atom, spins. Not in the way that the Earth spins on its axis, but in a rather strange way, to the extent that an electron, when we are not looking, is spinning both clockwise and anti-clockwise at the same time. It sounds like, oh, you know, you boffin physicists come up with all this nonsense. How do you know that's what really happens? And without that, we wouldn't have so much of modern science. Any one of you who uses any device, smartphones, TVs, computers, anything with a chip, all rely on quantum mechanics. Without quantum mechanics, we wouldn't have understood the nature of matter. We wouldn't have understood the nature of semiconductors. Therefore, we wouldn't have developed chips. We wouldn't have computers. Most of modern technology today relies on quantum mechanics. And yet, at its heart, it's very, very strange. Well, I've said, you know, biology at its heart is chemistry, and chemistry is basically quantum mechanics. So surely biology ultimately relies on quantum mechanics. Well, it does rely on quantum mechanics in the sense that quantum mechanics describes how the atoms fit together to make the molecules of life. But this new field, this field of quantum biology, is really asking whether the weirder aspects of quantum mechanics play a role in biology.
Now, quantum physicists have had almost a century to get their heads around this, and in a way they have, because the mathematics of quantum mechanics is perfectly well developed, and it's very powerful and predictive, and it helps us explain the subatomic world. But we've got something like half a dozen different ways of explaining how those atoms get through the slits. None of them are very satisfactory. The standard one, believe it or not, the standard way of explaining it is to say, don't worry your pretty little heads about how that atom does it. You can never know. All quantum mechanics ever tells you is it makes predictions about the results of experiments when you go and observe something. So quantum mechanics will indeed, the mathematics will tell you, if you're not looking, you'll get the interference pattern. If you're looking, it'll disappear. And hence you hear, if you've like in popular science, talking about the role of the observer is central. And it leads to all sorts of wacky ideas like, you know, in the nature of consciousness and so on in quantum mechanics. So quantum mechanics is weird. There's no getting around it. It's not that it's just weird in biology. It's weird for physicists. And it's sort of time that physicists let the biologists know that, you know, we've had all these years of sleepless nights and worrying how atoms do these things. It's about time you know, got very, very concerned about the subatomic world. One process that I have been interested in recently is called quantum tunneling. And I would say it's sort of halfway between mundane quantum mechanics, which is the rules of quantum mechanics that you have to apply in organic chemistry to describe how molecules fit together, including those molecules in living cells, and the more outlandish quantum behavior, superpositions and entanglement and so on. Quantum tunneling is the process whereby a quantum entity, a quantum particle, can somehow punch its way through a barrier, a force field, an energy field that it has no right to be able to get through. In the everyday world, it's the equivalent of me running straight through that wall, disappearing and appearing on the other side. It doesn't happen. In the quantum world, it seems that it does happen, and in fact, the picture I've got here is of the sun. The reason the sun shines, therefore the reason we are here, is thanks to quantum tunneling.
And what was happening is he's got a lot of mind power. Like, this guy is really powerful, and he was throwing everything at me, and that's why I was having this heat exchange, because my light was shining, you know, not as in blinding light, it was just my energetic pattern was really strong, and he couldn't stop me. And I ended up walking through walls in that state of being. It's not a dream. When we're in that higher awareness, we can do anything, right? We have the whole universe at our disposal. Yes. So I want people to know what we're capable of. Anyone in that state can do this. This isn't Special George, okay? Playing the hero here, right? And I walked through the walls, and I ended up walking straight up to him, finding him where he was. I seeked him out, and I confronted him. And I said, "Now do you understand?" And he said, "Yes." There was no words need to be said. It's because he threw everything at me, and he was just in a slump like that energetically. I said, "Now do you understand?" It was like I was showing him what we're capable of, and I showed him that you might think you've got it over us all, but when we want to activate ourselves, and I want people to know this is not a fantasy story. I want you to know that I lived this experience to come and tell you people that what we're capable of is amazing. We can do anything.
And for us, quantum teleportation might explain sometimes when people go a great distance in a very short period of time. These are the kind of stories that have often been reported through realityshifters.com. Another exciting possibility, of course, would be quantum coherence, which enables us to finally have an explanation for synchronicity and for coincidence. And last but not least, that superposition of states in which you can have both a 0 and a 1 at the same time. This enables us to start having a mechanism from which we can explain things, including spontaneous remission of disease, near-death experiences, and lucid dreams, where we really physically get a sense of experiencing other parallel universes and realities. So, welcome to the quantum age. This is Cynthia Sue Larson with realityshifters.com.
Hello, this is Cynthia Sue Larson with realityshifters.com, and today I'd like to talk to you about the idea of sudden jumps, big changes, and they can occur everywhere. I'd like to start with a quote that comes from the TV show Shameless. This is from the Frank the Plumber episode, Season 3, Episode 9. It says, "Great things don't happen in tiny little increments. You know they happen when someone thinks completely differently. So when we think about that, we get the idea, or I do, because I'm now speaking to you from the Boulderado Hotel in Boulder, Colorado. I think about history. This hotel is like a museum. It's got pictures showing a great flood when Boulder Creek flooded over 100 years ago, things like that. So when we think about history, think about the time in this hotel when guests came in horses and buggies and carriages before the car, and the firemen didn't have a fire truck. They were doing things on foot. This is extraordinary. When we think about that, we get the idea that sometimes we have witnessed in our history when there's been a big change. We don't see the in-between phase between horse and buggy and automobile. And maybe it existed, but most people didn't have it. Why bother with that when you can go straight to the automobile? Turns out nature thinks very similarly, and I have spoken about that previously, so I'm not going to go into the E. coli bacteria and the way that it could instantly make a huge evolutionary change and basically evolve itself into a form of bacteria that could then digest the only food presented to it that it could not eat before, lactose, which is what the scientists were giving it. So if we think in terms of evolution, a lot of us have believed, as Darwin proposed, and according to classical physics it makes sense, that instead of these huge steps, these huge jumps of evolution, where there are missing links, you've heard that phrase, we would expect to see lots of little in-between phases where a species would evolve gradually. That's not, in fact, what we're finding in the laboratory right now with bacteria. It's not what we would expect when you're thinking in terms of the quantum computers that are being built and you recognize all of the quantum phenomena are quite possibly occurring at every level of reality. That's the big idea that I'm presenting to you. And actually, what I'm saying is that phenomenon where you see someone alive again, such as I first reported in print in 1999 in my book Reality Shifts, When Consciousness Changes the Physical World. I think it's important for people to realize this phenomena is not just now happening, just as the Large Hadron Collider is firing up. No, it's been around for what I'm saying is millennia. And we can see proof of this if you start looking for it that way, and you view the archaeological record, and you view evolutionary jumps as being quantum jumps. Instead of looking for the tiny little step that makes it look like a slope, so you start looking for these huge jumps. It's a staircase with giant steps. That is what we would expect to see in a quantum universe, which is what I believe we have. That's also what I'm saying is happening in all fields of all of our sciences, from cosmology to biology to chemistry, you name it. Until next time, this is Cynthia Su Lárson talking to you from Boulder, Colorado, and I'm with realityshifters.com. Thank you.
But before we start, why don't you explain to people out there what a reality shift is?
Yes, a reality shift is when something appears, disappears, transforms, or transports, or it can be a change in the experience of time. So it's basically any number of things, including synchronicities, coincidences. It could be spontaneous remission of disease.
So why don't you explain in the scientific part of it what happens?
Okay, well, that's a good question. What is happening? And there are several theories. What's happening when we look at what's going on that level is we're noticing basically quantum physics behavior occurring at the macro level. So we're noticing what Einstein once called spooky action at a distance, where you can see that there's entanglement of quantum particles. So I know I don't want to get too much into all this, but basically things are very strange at the quantum level because basically that's the place where you can see the fundamental building blocks of matter, which don't even behave like matter. They behave more like energy half the time, at least. So there's a wave nature to all of this so-called physical reality that we take for granted. And you wonder, what level of reality are you operating? And so people that meditate, they get a sense of themselves that's much bigger than the ego sense of self that we often have. So when I talk about ego, I just mean the small I, the sense that that I was born, I will die, that I only have control over a certain small number of things. When you identify with a part of yourself that's much more timeless and much more independent through time and space, then these kinds of experiences that I call reality shifts are commonly encountered by people, for instance, in Tibetan Buddhism, when they follow a spiritual path. What's happening when we look at what's going on that level is we're noticing basically quantum physics behavior occurring at the macro level.
So what if we got here?
So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. You see, this is quantum trapping.
That's amazing.
As long as it's
so
cold,
it's superconducting. It's frozen with liquid nitrogen.
It upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnetic field in 3 dimensions, right?
Yeah, exactly.
And that
pivots.
You
see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
it stays there on the X and Y, but not on, it pivots on the...
Yeah, on the axis of the magnets. You see, if I can move it on the side, it will again pivot around the axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing. Can you put it on the track for us?
Yeah. I just levitate it above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it at an angle and it would still fly around.
Yeah, I can do it like this, and it will just go around like this. Because I go and put it at different height, and then like this.
And lock it at the height.
Lock it, yeah, different height, different configuration.
Right.
And I can even lock it at opposite way. If you could just hold for a minute. High. I'm doing the same thing. I'm locking it upside down, and then it is suspended.
Fantastic. Okay.
The phenomena you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So, a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating currents. Now, the combination of both effects, the expulsion of magnetic fields and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomena. It's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipates energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in midair. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down, and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see? I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So we have quantum locking, and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disk. But that's not the amazing part yet, because there is something I haven't told you yet. And and the amazing part is that this superconductor that you see here is only half a micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disk on top of this rail, it moves freely. And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disk and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended. You see, it's quantum locking, not levitation. Now, while I'll let it circulate for a little more, let me tell you a little bit about superconductors. Now, so we now know that we are able to transfer enormous amount of currents inside superconductors. So we can use them to produce strong magnetic fields, such as needed in MRI machine, particle accelerators, and so on. But we can also store energy using superconductors, because we have no dissipation. And we could also produce power cables to transfer enormous amount of current between power stations. Imagine you could back up a single power station with a single superconducting cable. But what is the future of quantum levitation and quantum locking? Well, let me answer this simple question by giving you an example. Imagine you would have a disk similar to the one I have here in my hand, 3-inch diameter, with a single difference. The superconducting layer, instead of being half a micron thin, being 2 millimeter thin, quite thin. This 2 millimeter thin superconducting layer could hold 1,000 kilograms. A small car in my hand. Amazing. Thank you.